Hello and welcome to our next lesson for advanced. Today we are going to look at what is known as Euler's number, named after mathematician Leonhard Euler. Note it's pronounced Euler and not Euler, which is one of the common mistakes, much like it is the sine rule, not the sin rule. This is Euler's number, not Euler's number. All right, so let's get into it. So we have been looking at exponential functions. We're carrying on with that. Note that for any normal function that's not exponential, where we've got y equals x to the n, if we find the derivative of that, we find the gradient function, and that's going to be of some form nx to the n minus 1. Remember, we take 1 away from the power, and then we bring that out the front and multiply it by whatever that power originally was. What this means is that we go from example, a cubic function down to a quadratic. Or if we started with a quadratic, we'd go down to a linear function for its gradient. So every single function, when we find the derivative of it, we go down a degree and it changes. That is not going to work for exponentials, right? Exponentials are different. What happens with exponentials is that the gradient stays as an exponential function, right? So the derivative of an exponential is an exponential, right? That's not going to change. So we've got a little diagram there on the screen. What we've got is the blue function. Now, if I look at that, we can see it goes through the point 0, 1, and then it goes through the point 1, 2. Hopefully from the previous lesson, we should be able to recognize that that's the function y equals 2 to the power of x, or as I've labeled it here, f of x equals 2 to the x. That green line is actually the derivative of f of x. So we can call that f dash of x. Now, what it actually is isn't important at the moment, but the point is that that green line is the derivative of the blue line. Similarly, here we can see there's a blue line and a green line, but they're almost touching. But note that before we had the blue line to the left, and then the derivative was to the right, whereas here we've got the blue line to the right and the derivative is now to the left. So again, if we look at the blue line, we can see that it goes through the point 0, 1 and it goes through the point 1, 3. So therefore this is, let's call it g of x, is equal to 3 to the power of x. And now that green line is the derivative. So what's happened there is that derivative has crossed over somewhere between 3 to the power of x and 2 to the power of x. That line of the gradient, which is an exponential, will be exactly the same as our original exponential function. That specific base is Euler's number, right? So this is a special exponential, and it's the only exponential where this works, that the original function has a gradient function that is exactly the same. So that orange line is both that equation, y equals e of x, and the derivative of that line, which is also y equals e to the x, right? It's the only situation where the gradient of a function is exactly the same as the initial function that we started with. If you can find this on your calculator, you'll have a button that's e to the x, and if you type in as x is 1, the calculator comes back with Euler's number, 2.71828, and so on and so forth. Right? E is irrational, just like pi is. It is a non-recurring, never terminating decimal that just goes on forever. Much like pi, its computers have been used to calculate the value of e to million decimal places. There's no need for that piece of information to how far it goes to. We don't use e as far as the actual value of e that often, but we use e as far as Euler's number in finding exponentials. And you will see we will use e more and more as we go on through with advanced. Okay, so let's look at an example. So we've got a population of salmon living in a river, and we can model that population using an exponential function p equals to 200e to the power of 0.3t, where t is time in years. All right, so that's our equation that we're going to use to model this particular population of salmon. So what we need to first find out is, what is the population going to be after 3 years? Right, well, we know that t is time in years, so if we wanted to do that, we can just substitute in 3 for t. So when t is 3, we get p equals 200 lots of e to the power of 0.3 lots of 3. We can type that straight into the calculator. Remember, I did say you have got a button on there that's e to the power of x, or depending on your calculator, it might be e to the power of n. Sometimes it's just e to the power of a square. It totally does depend on your calculator. I'm looking at the Casio calculator that most of you should have. It's in the top right hand corner, just underneath the X exclamation button. So you're going to need to press Shift and then the button that looks like in. It's actually LN. Shift LN will give you e to the square, and then you can type in your value. So you can just type that in exactly as it's written into your calculator, and you will get that p will be 492. So after 3 years, our population of salmon, 492 fish. Yes, that has been rounded up to the nearest whole number. All right, we can't have 0.9 of a fish. We need to round up, right? These or down appropriately. But the point being, we need to have whole numbers when we're talking about a population. Part B, we want to draw a graph of this particular population. In a situation where you're having to do this on paper, you would have to plot points. All right, so we're going to start off with t is 0. There's no point doing negative numbers because this is a population. We can't go backwards in time. We're going to start with 0. So when t is 0, we get that the population is going to be 200. Now, hopefully, you should be able to look at the formula and realize that that number in front of the e in any situation, so long as we haven't got a constant on the end after that, but if it's some amount multiplied by e to the power of something, that amount is going to be our initial population. Right? When t is 0, e to the power of 0 becomes just 1, so it's just 1 times whatever that number out the front is. So our initial population is that 200. If we had an equation of, let's say, 5,000 e to the negative 6t, well, then that number before the e is going to be our initial population. All right, so we've typed in 0 and we've got that initial point, 0, 200. Next thing we're going to do is say, well, what's it going to be when time is 1? We substitute 1 in, and we get that our population is going to be 270. So after 1 year, we've got 270 salmon living in this river. Substitute in 2, and we're going to have, after 2 years, our population is 364. And from part A, we already know when t is 3, we've got 492. So there are 4 points that we can plot on a set of axes. Now we know this is an exponential because it's got the e in there, so we know that these points need to curve. All right, we're not going to draw in straight lines between each of those 4 points. It needs to nicely curve. And I've used Desmos. Either way, you should get something that looks like that. All right, we're starting at 200, that's our initial population, and then it's going up over time with a bit of a curve. Purely because of my x-axis is only going up by 1, but my y-axis there, the grid's going up by 200. We don't see a huge amount of that curve, but you can see it's still got a bit of a curve there. Like I was saying before, if you are doing this on paper, that's what you would have to do. Put in points, work out what they're going to be, plot them, and then connect them up. At this stage, I'm more than happy for you to use any sort of graphing software, Desmos, GeoGebra, anything like that. It's totally fine, so long as you understand what each of those components in the equation do. But otherwise, that's it. That's all this lesson is. It's just getting your head around the whole idea of what E is and how it works in a calculator to get out values of E and what function it serves within an exponential. Right? You don't have to worry about anything else at this stage. That's all we're looking at. Just playing around with exponentials and the value of E. As always, any questions, feel free to email me or on Google Classroom. Nice short one today. I hope you're all doing well, and I will talk to you next time.